Hello and welcome to a demonstration on how to graph rational functions when you are given their algebraic forms. This slide show's purpose is to demonstrate how to obtain a graph of a rational function from an algebraic description. Some materials for review include finding domains of rational functions, setting the denominator equal to 0 and solving. We would also like to determine the intercepts of rational functions. X-intercepts are found by setting the numerator polynomial equal to 0 and solving. Double check to make sure the value is in the domain. Y-intercepts are found by substituting x equals 0 into the rational function and simplifying. Again, double check to make sure 0 is in the domain. We would also like to determine asymptotes of rational functions. This refers to all types of asymptotes, the vertical, the horizontal, and the oblique. Now, vertical asymptotes make the denominator 0, but not the numerator. This is how you identify vertical asymptotes. Horizontal asymptotes occur when the degree of the denominator is greater than or equal to the degree of the numerator. If the degree of the denominator is greater, then y equals 0 is the horizontal asymptote. If the degrees are equal, then the ratio of leading coefficients will be the horizontal asymptote. Oblique asymptotes occur when the degree of the numerator is greater than the degree of the denominator, and these are found by performing division and consider the quotient. The remainder will have a degree strictly less than the denominator via the division algorithm. And one last thing we would like to determine are holes of rational functions when they are present. Holes occur when the root of the denominator is also a root of the numerator, and this leads to a 0 over 0 form, which is indeterminate and not undefined. This implies that more investigation is needed, and the steps to investigate further are listed here. Reduce the rational function by canceling that duplicated factor. Substitute the x value into the reduced form. This x value is the factor or is the number that made both the top and bottom equal to 0 in the original rational function. If a numerical value occurs, then you have a hole. And again, the x-coordinate will be the value that makes both the denominator and numerator equal to 0 in the original rational function. The y-coordinate is the value that results when using this x value in the reduced form of the rational function. Now, some additional notes on the examples forthcoming are as follows. The generic symbols used in this presentation when needed are r of x for rational function, n of x for the numerator polynomial, d of x for the denominator polynomial, and r bar of x for the reduced form of the rational function. And these are all capital letters. If you have trouble remembering the conditions for horizontal asymptote or oblique asymptote, go ahead and perform division of the rational function. The quotient will be the horizontal or the oblique asymptote. The guidelines that are presented here for horizontal and oblique asymptotes are simply shortcuts that result from this division. So you may think of horizontal asymptotes as a very special case of an oblique asymptote, but they are all found by finding the quotient of division. Okay? Vertical asymptotes are found by setting the denominator equal to 0 and making sure those values do not make the numerator 0. So that's a different procedure for finding vertical asymptotes. And one final note here is that complex solutions of any kind are not considered here as part of the graph because we are graphing in the real plane. If a complex number is required to make either the numerator or denominator equal to 0, we go ahead and discard it here. So our first example is we have a rational function. R of x is equal to x plus 1 divided by the product of the quantities x minus 1 times x plus 2. We're going to proceed as follows. We identify the domain. We set the bottom equal to 0 and solve. Fortunately, it's factored for us already. So we find that x cannot be equal to -2 and x cannot be equal to 1. If it does equal -2 or 1, we have a 0 in the denominator, and that's not allowed. So now when we look around x equal -2 and we look around x equal 1, the graph becomes unbounded. This implies that x equal -2 and x equal 1 are vertical asymptotes. Now, vertical asymptote at x equal -2 implies that x plus 2 is a factor of the denominator, which we see, and the odd multiplicity of the root implies a change in the sign. This again comes from polynomial theory and the multiplicity of roots for polynomials. The vertical asymptote at x equal x equal 1 implies that x minus 1 is a factor of the denominator. And again, we can see that in the original form. The odd multiplicity of the root implies a change in the sign here as well. So what's going to happen in our graph is that as we cross over, reading the graph from left to right, as we cross over those vertical asymptote locations, the output, the rational function, if you will go ahead and change sign. If it was positive on the left side of that vertical asymptote, it's going to be negative on the right side of that vertical asymptote, and vice versa. So let's take a look and see what we have right now. So right here, we have our vertical asymptotes, and they are drawn in red, and they are dashed because they are not an actual part of the graph. There is a horizontal asymptote at y equals 0 because the degree of the numerator is less than the degree of the denominator. This can be determined by adding the multiplicities of the roots in both the numerator and denominator, or we may simply count up the number of factors in this case. The x-intercept of the graph is -1, 0. The graph crosses the x-axis at this point because it is a root of odd multiplicity in the numerator. The y-intercept is determined by substituting 0 in for x into our rational function. And when we do this, we end up with -1/2. So there are points on the graph, and these points are located at -1, 0 and 0, -1/2. So we're going to go ahead and plot those next. So here in blue, we can see the horizontal asymptote at y equals 0. And again, it's a dashed line because it's not a part of the actual graph. We also have the points -1, 0 and 0, -1/2. These are the x and y intercepts respectively that we determined by solving the numerator for the x-intercepts and substituting 0 into the rational function for the y-intercept. Now what we're going to do here is we are going to start building our graph. And we do this because now we have all the information that we need in order to sketch the graph. Now we know that rational functions are continuous over their domains. So we also know that from this x-intercept to the y-intercept, it has to be connected. So there's a rough sketch there. We also know that because x equal 1 is a vertical asymptote, as I get closer to it, I have to go off to an infinity. But I can't go off to positive infinity in this case, because that would mean I would have to cross the x-axis again. There would have to be another solution to the rational function, and there isn't. We already found them all. That means that from the y-intercept, as I get closer to the dashed vertical line at x equal 1, I have to get closer and closer to negative infinity. So I go down this way. Now we found out that x equal 1 was a root of odd multiplicity in the denominator. That means it changes sign. So as I go to the right side of this red dashed line, this vertical line, I should be in the positive range. And I know that when I get close to x equal 1, my graph should be getting closer and closer to positive infinity. So I know that part. And as I go further and further away from the origin, as I go further away from the origin here, I should be getting closer to the horizontal asymptote. In this case, that blue dashed line on the x-axis. So I'm going to just sketch out a graph that gets a little bit closer. So it's going to look something like that. I will not hit this horizontal asymptote, again, because that would imply there's another solution, which we know there isn't. Also, the remainder, when you actually do the division, the remainder doesn't have the possibility of having any solutions. So this is what some of it looks like right now. Now we know, coming over to this other side, we know that at -1, 0, that was a root of odd multiplicity. And that means that I'm going to cross the x-axis again at this point. And again, as I get closer to x equal -2, I have to get close to a positive or negative infinity. Well, I can't get close to negative infinity in this case because that would mean I would have to cross the x-axis again. That would mean there's another solution, and there isn't. So that means that from this x-intercept, I have to get closer and closer to positive infinity. That means I have to go up like this. We know that x equal -2 was a root of odd multiplicity in the denominator, and that means that, again, we have to change sign. So I was positive over here. Now I'm going to be negative. And again, because I have to be approaching negative infinity in this case, my graph is going to be close to negative infinity when I'm close to -2. So I'll go ahead and draw that part. And as I get further away from -2, I'm going to get further away from the origin as well. And that means I have to get closer to the y asymptote, the y equals 0 asymptote, the horizontal asymptote. And that means that my graph will look something like this. As I get further away from the origin, I'm going to get closer to the x-axis. I won't hit the x-axis, though, again, because that would imply there's a solution, and we know there isn't. So my sketch is going to look something like this. Now, we know there are no oblique asymptotes since we have a horizontal asymptote. Remember, you can only have one or the other. You can't have both. That's a result of the division algorithm. And there are no holes in the graph, since no roots were shared in the numerator and the denominator. So essentially, my sketch is done. And using technology, we end up with a sketch that looks something like this. So when we examine our sketch, we find that we have this kind of a sketch going on, with this kind of picture. And when I examine my technology, which graphs it much more accurately, we see that my sketch is, consistent with what the technology is showing us. So this is how you can go through and apply the information that we find in the process in order to sketch the graph of a rational function. Thank you for your time and attention.